Alright, now I apologize. This is a long assignment. It's probably going to take us a while. So let's try this first one. Okay, I want to know how high the Linearized bridge is. I use real values. So an object falls for 3.4 seconds. We're going to use d equals 1/2 at squared. Don't forget it's squared. So here you go. Alright, so the distance is going to equal half of the acceleration. So that's 5, because 5 is half of the acceleration of 10, which is what we have for gravity on Earth, times 3.4 squared. Don't forget to square it. And what that gives us is the distance from the Linearized ridge to the bottom is 57.8 meters. Okay, I'm on a weird planet. I'm on a 602 meter high cliff. That's going to go in for distance. So 602 is the distance. I'm looking for what is the acceleration of gravity on this planet. Now watch this. That means I'm solving for 1/2 a. I've got to be careful because that's half of a, not all of a. And the rock took 21 seconds. So I'm going to say times 21 squared. So what I need to do first is I'm going to square 21. And if I square 21 squared, I'm not sure what that equals. But all I know is I'm going to divide both sides by 21 squared. 21 squared. And then when I do that, what I'm left with is 1/2 of a is equal to 1.365. And therefore, how do you undo taking half of a? You multiply it by 2. So I multiply this by 2, and what I find is the acceleration of gravity on this weird planet is 2.73 meters per second. Okay, now I've got a tightrope walker. I'm just going to read through this. What the question is: how long does she have? So I'm looking for time. That means I must know everything else. So the distance is 45 meters. And that equals half of a. So this is on Earth, I'll assume. So half of a is 5 times t squared. Well, that's not a very good t. So that means I have to divide both sides by 5. Alright, which makes this one go away. And now I want to undo squaring this. This is squared. The opposite of squaring is to take the square root. So if I take the square root of both sides, what I'll get is that 45 divided by 5 is 9. I'm taking the square root of 9 equals t. Therefore, t equals 3 seconds. Alright, let's move on up here. Okay, a car locks its brakes. The skid mark is 27 meters. Meters is distance. So I'm going to say 27 meters equals, and the question is, how much negative acceleration is the driver subjected to? So I'm going to be solving for 1/2 a, and the time was 4 seconds. Don't forget, it's not 4, it's 4 squared. Well, 4 squared, as I'm sure you know, 4 squared is 16. Let's see. So I have 27 divided by 16. Well, let's go ahead and divide this by 16 also. So that gives me is 27 divided by 16 is 1.68, 75 or something like that. That equals, don't forget, 1/2 of a. It's easy to forget it's half of a, but now what I want to know is what is all of a. So what's the opposite of taking half of a? Well, it's multiplying it by 2. So I have to multiply this by 2 to find out what all of a is. In this case, a equals 3.375, what is it called? 3.4 meters per second. The next question is, how fast is the car accelerating? So it's another one of these problems. These are real numbers here. So what I've got is a track that is 400 meters long. That equals half of the acceleration times the square of the time. Now the time is 4.8 seconds, and it's going to be d equals 1/2 at squared. So then I just have to divide both sides by 4.8 squared. 4.8 squared divided by 4.8 squared. And then let's see, that equals, that means that, well, first of all, this cancels out. 400 divided by 4.8 squared is 17.36 equals half of a. So therefore, all of a equals twice that much. I have to multiply both sides by 2, and I'll get the acceleration is 34.7 meters per second per second. Let's keep going here. Alright, now here comes a linearization problem. So I have basically time and distance data for a motorcycle that's accelerating down a track. Now if I was just to graph it as distance versus time, I get this curved value that's exponential because it's t squared. But to linearize, I want to find the acceleration. That means I need to turn it into a straight line. And this trick called linearization is something that's very popular in physics classes. And what it does is once you determine what type of relationship it is, in this case t squared, instead of graphing t, I'll graph t squared. So that means I have to take these time values and square them all to see what it's going to be. So 0 squared is 0, 2 squared is 4, 4 squared is 16, 6 squared is 36, and 8 squared I believe is 64. And so remember what we're solving for here are these values are t squared values, and if you notice on a linearized plot, that's when I plot as t squared rather than t. So what I want to do is this: I want to say, okay, at t squared 0, distance was 0, so I'm going to put a dot right here at 0, 0. Now at a t squared value of 4, I am going to go a distance of 17. So this can be a little bit tricky here. So let's see what we're counting by. If this is 100, we got 5 spots, so we're counting by 20. So 17 will be just below this one. And this is 20, so we're counting by 5, 10, 50. So we're counting by 5, so I'm going to be, this next plot is going to go pretty much right about here. Alright, and then we're going to go to a time squared value of 16 and a distance of 62. So I'm going to go over to 16, which is going to be here-ish, and I'm going to go up to 20, what am I going to do, 20, 46, so I'm going to go up right about here. So I put one there, 16 and 20, 40, 60, so right about here. And look, it's starting to line up, isn't it? If you notice, it's starting to line up. Now, that's what we call it linearizing. I'm going to go to 36, and I'm going to 146. So I'm going over to 36, which is going to be about here. And I'm going up to 146, which would be about up here. So, let's see, 36 and 146 is 100. I put it right about here. Alright, and then I'm going to go to 64, a t squared value of 64, which is over here. And I'm going to go up to 250. So I'm going to 64, and then 2, let's say 2, right about here. Okay, now what I'm going to do is I'm going to draw a best fit line, which is going to be hard to do on this computer thing I'm holding, but I'm going to try. I'm going to do it in red ink. Okay, so here is my best fit line. Hey, I did pretty good, I thought. Look how it lined up. It linearized just fine. So now what I do is I find the slope of this line. So, and the slope of this line is going to be, let's see, I'm going to pick a point of intersection right here. I'm going to say 200 divided by, let's see, that's 4 divided by 50. 200 divided by 50 is 4. What we had to remember now is 4 is not the answer. That is the slope of the line. So the slope equals 4. But the slope in this case, remember the equation we're dealing with is d equals 1/2 at squared. Now if you think, this is d, here's d, right here, here's t squared, that's here, so this is what the slope is. This slope equals half of a. That equals 1/2 a from the equation, d equals 1/2 at squared. So what is all of a? It's 8 meters per second per second. What just happened? Alright, now we're going to make things a little bit trickier. We're going to have falling objects start with a non-zero velocity. So we're going to use this equation here. D equals 1/2 at squared plus velocity times time. The initial velocity times time. So what we've got is we want to know how high the bridge is. So we're trying to solve for D. That's easy. Half of A is still 5. The time is going to be 4.4 squared. That's the d equals 1/2 at squared part. But then we're going to add the initial velocity, which is right here. It's 23 times, we'll do it this way, times 4.4. So what that gives us then is d equals, well, 5 times 4.4 squared is 96.8 plus 23 times 4.4 is 101.2. So therefore the distance traveled is 198 meters. So think about it, if I hadn't shot it downwards, it would have gone 96.8 meters, but the velocity I imparted gave it an extra 101 meters. Alright, let's try another one. This second one, it says, how deep into enemy airspace is it in 45 seconds? So really, in this case, again, we're looking for distance, so, but this is a non-gravitational acceleration. Shouldn't matter. D equals 1/2. Now the A in this case, let's see, here's my acceleration. Accelerate at 19. So it's going to be 1/2 of 19 times the time it went for was 45 seconds. There's my time. So I'm going to say times 45 squared plus, how fast was it going initially? Well, it was initially going 234, and I'm going to multiply that by 45 seconds. So it's just like the last one. So what I'll have here then is I'll have D equals, let's see, 1/2 of 19 times 45 squared. That's like 19237.5 plus we have 10,530, and I just add those all together, and I come up with 29767. 29767.5. Let's not forget that that's half of a meter. Alright, let's see what happens next. The next one, ooh, now I said how fast. Remember, fast is velocity. So I'm looking for the v part of this. Okay, so I must know everything else. So let's just see. Alright, here's my distance, 134 meters. So I have 134 meters equals, now here we are with gravitational acceleration on Earth. So that's going to be half of a is 5 times t squared, that's 3.3 squared plus, and then it's going to be v times 3.3. Okay, so now we're looking for this. So let's see, I'm going to say 5 times 3.3 squared is 54. So that's 54.45 plus v times 3.3 equals 134. Now what I have to do is I have to take 54.45 away from both sides to get this one to go away. So I take 54.45 away from both sides. What I get is 79.55 equals v times 3.3. Now to get it by itself, I have to divide both sides by 3.3. Whoops, what just happened? I'm going to divide both sides by 3.3. And what I get then is v equals 24 meters per second, which is a very reasonable velocity for an arrow coming out of a bow. Alright, let's keep going here. We're almost done with our homework. I'm looking for, we got the quadratic coming up. Yeah. Okay, so let's see, we got, let's see, number 13. I got this rocket. And what am I looking for here? How much negative acceleration is required. Okay, so I wonder how much is, we're trying to slow it down. So I'm solving for A. So, let's see. Here's the distance. It is 98,000 meters equals 1/2 of A times t squared, and t in this case is 194 seconds squared, plus the velocity it was going was 240, so it's 240 times 194. So now I got to get A by itself. So what I'm going to do is I am going to first, how do I want to do this? I think what I'll do first is I am going to take this right here away from both sides. So that's going to go away here, and then I'm going to take it away from here, and when I take that away, what I end up getting is 51440 equals 1/2 A times 194 squared. So now what I'm going to do is I'm going to divide both sides by, I'm going to divide both sides by 194 squared, and that's going to make this go away. Now that equals 1/2 of A. I don't want to know what 1/2 of A is, I want to know what all of A is, so that means I need to multiply both sides by 2. So I'm going to multiply this by 2, and that's going to make the 1/2 go away. And so what that leaves me with then is A equals, now by the way, this was a negative acceleration, so it's negative 2.73 meters per second Oh, here we come to it. The fun times couldn't last forever. Now I'm trying to find time. Alright, so here's what happens. I'm going to set up like I did before. I'm going to say, alright, I know the distance. 1485. Be a good dog, Bentley. Equals 1/2 of A, and let's see, we're talking about here on Earth, so that's 5. 1/2 of A is 5. I don't know what the time is, so it's t squared. But I do have to add the original velocity, which is 245 times t. So what I do now is I need to get it this way. I'm going to take this away from both sides. And when I do, what I get is this. I get 0 equals 5t squared plus 245t minus 1485. And that can be put into a quadratic equation because basically this is A, this is B, and this is C. And I know your math teachers have worked on this with you, so let's go ahead and put that in. What we get is therefore that t is going to equal negative b, so it's negative 245 plus or minus the square root of 245 squared. Now by that was a 45. Now figure 245 squared minus 4 times A, which is 5, times C, which is negative 1/2. 0.485, and we're going to put that over 2a, so that's be 2 times 5, which is 10. And we're going to solve that, and when we solve that, what we're going to come up with is 5.45 seconds. And our last one. Now we've got to be careful with this last one. What we've got is, here's how high the rocket is. Here's how fast it's traveling upwards. There's our V. And the burn moves the rocket to an altitude of this high. So really, it's a little bit tricky because neither of these is the values we're going to use for D. It's the difference between them. So the acceleration moved it from here to here. So the D I'm going to use is actually 9624. And it's a little bit tricky, but you're big boys and girls, you can handle this. Equals half of A. Well, A is 38, and half of 38 is 19, times t squared, plus the original velocity when this started was 1,200 meters per second. So 1,200 times t. Now what I have to do is I'm going to subtract this from both sides, which gives me 0 equals 19t squared plus 1,200t minus 9624. And what that means is here is A, here is B, and here is C. So we're going to use our quadratic again. And what that gives us is T is equal to negative B. So negative 1,200 plus or minus square root of B squared. So that's 1,200 squared minus 4AC. So 4 times A, which is 19, times C, which is negative 9624. And all of that is going to be divided by 2A, so that is going to be 38. And then this is a question of putting things in my calculator. And when I do that, what I find is that T equals 7.2 seconds. Well, there it goes. Hope you enjoyed the homework as much as I did. That took a while. Sorry about that.